Welcome to the next lecture. So, in this lecture we will continue with design of control unit, and we will till now what we have seen. We have seen single bus organization, both are internal to CPU, and multi-bus, which is a 3-bus organization, again that is internal to CPU. Now, we will be looking into how we can execute various kind of instructions. We have only executed one instructions, one complete instructions. Now, we will look into how we can execute various kinds of instruction using single bus architecture, a typical single bus architecture. So, for this what we have done, we have selected a set of 12 instructions, and we will discuss the control signals required to execute these instructions on a single bus processor architecture. So, for showing the control sequences, control signals for various instructions, we have chosen these set of instructions. So, this set includes add with register, add with memory operand, loading a word, storing a word, moving data between register, moving an immediate data to a register, unconditional branch, conditional branch, increment R1, decrement, so increment operation, decrement operation, and compare, and of course halt. So, we will concentrate showing the various control signals that are required to execute the following set of instructions. Let us see this. As we know that for all the instructions that I will be showing you, the first 3 steps will be the same, and all the instructions I have taken single bus architecture to show all the instructions. So, let us see this. PC out, MAR in, read, select 4, add, Z in. So, these set of control signals needs to be activated at time step T1 for execution. So, what it will do? It will output the value of PC into the bus, and then it will be put into MAR. Then we activate the read control signal. At the same time, we select 4, PC out, so it will be available to the B input, and when we do select 4, then the A input will be having 4. We perform add, and after addition we put the result in Z in. Now, the incremented value of PC is in Z in. We do Z out, and we again put it in PC using PC in signal, and then we also put it in Y in. We will be seeing that in course of time why we are putting it in Y in, and then we wait for memory function complete. In the next step, we do MDR out and IR in. That means, after the memory function complete is set by the memory unit, what we can do is that we know that the instruction is now available in MDR. Once the instruction is available in MDR, it can be brought into IR. Now, at this stage it is ready for decoding and execution. So, from the next step, the instruction get decoded at the end of this, and after decoding it is ready for execution. So, this instruction basically adds the content of R1 and R2 and store back in R1. So, for this, one input should directly come through bus and the other input should come through Y. So, we are doing R1 out, Y in. So, one of the register value is coming through Y. Next, we are doing R2 out, select Y, add Z in. So, now R2 out is available directly from the bus. We perform select Y, Y will get selected, we perform add and put the result in Z in, and finally we do Z out and the data is now available in R1, and finally end. Let us move on. Now, this is for a extra memory access. So, what this instruction will do? It will load the value from location A from memory, it will add it with content of R1 and it will store back to R1. Let us see how we can do it. Now, I will not be repeating this again because first 3 step is again the fetch, which is same for all instructions. Let us see from next step what we need to do. Just understand what we need to do. In the first step, this is a memory location. So, this particular value should be put in MAR and we need to activate the read control signal. Once wait for memory function complete signal will arrive, then the data available in MDR will be brought in, added with R1 and will store back in R1 again. Let us see what are the steps that are required for this operation. First, you need to make available this. This can be available from the address field of IR out. So, address field of IR out will make available this content, which goes to MAR in at the same cycle and we perform read. We activate the read control signal. After this is done, then it is hit to the memory and it start reading the data. In the next step, we need to wait for the memory function complete. So, we are waiting for memory function complete. At the same time we are waiting for memory function complete, we can also make available the value of R1 into Y. So, we can do R1 out, Y in. So, R1 value is now available in Y register. Next, what we do? After this memory function complete signal is provided by the memory, then the data will be available in MDR. We do MDR out, we do select Y because already in Y R1 value is present, we perform add and we do Z in. So, after performing this Z in, the result is now in Z in, Z register, but the result has to be in R1. So, we perform Z out, R1 in and finally we end. Next, let us see the instruction to load the value from a memory location. We already did it in the previous instruction, but just for loading, let us see what to do. In the same case, first 3 steps will be same and from the 4th step, this will be present in the address field of IR out, which is put in MAR. Using MAR in, we activate the read control signal and then we wait for memory function complete. Once memory function complete is performed, then the value is available in MDR and from MDR we have to put it in R1. So, we do MDR out, R1 in and we end for loading a word from memory. Let us move on how to store a word into memory. Now, for loading a word, once we activate the read control signal, the data is read and it is stored in MDR. For write operation, similarly, we know that we have to put the address in MAR and the data that needs to be written will be put it in MDR and then only we can activate write control signal. So, we need to do these 2 things. Earlier we were just putting the value that the address that needs to be read into MAR and we were activating write control signal, read control signal. But for write, you need to put the data in MAR as well as in MDR and then you activate the write control signal. So, what we are doing here from step 4, address field of IR out, MAR in, R1 out, MDR in. because the content of R1 needs to be written into LOCA. So, R1 content should be in MDR and we activate write control signal. And in the next step, we wait for memory function complete. After the memory function complete has arrived, then we can end it. This is very simple, moving R2 to R1, content of R1, R2 will be moved to R1. So, R2 out, R1 in. The content of R2 will be moved to R1. Many cases we require to store an immediate value into a register. So, immediate value is stored in the immediate field of IR out. So, the immediate field of IR out value we need to put it in R1. So, we simply do immediate field of IR out comma R1 in. So, value of this which is 10 will be moved to R1. Now, coming to branch instruction. So, in branch instruction, in unconditional branch, what happens? In unconditional branch, there is no condition. If branch is there, we need to load the PC with the branch address. So, we know that every time we fetch an instruction, what happens? After we fetch an instruction, the PC value gets incremented to point to the next instruction. In any instruction, either it is a branch, add or any instruction, in the fetch phase we do not know whether it is a branch instruction or not. So, in any case we are incrementing the PC value, but after decoding the instruction we will be knowing that this is a branch instruction. Once I know after decoding that this is a branch instruction, then what we need to do? We need to load the value of the PC with the branch address. That needs to be calculated first, that offset, and then it should be loaded into PC again. So, let us see what are the steps that are required for this purpose. Now recall our discussion where we said that in step 2, what we are doing? We are doing Z out, PC in, and we are also doing Y in. And I told you at that point that this Y in is required for branch. Now, let us see why it is required for branch. Branch to label, that means content of the PC value should be added or subtracted depending on the offset, and we get a new PC value where we have to go and fetch the instruction. So, in this case what we are doing, offset field of IR out will be available, and if we select Y, because you see in Y PC value is incremented, PC value is already there. So, in Y as incremented PC value is already there, we need to add that PC value, incremented PC value with the offset such that now the new PC should be this added one, content of PC plus the offset. So, that is what we are doing. Offset field of IR out, select Y, because Y in already contain the updated PC value, we add and we do Z in, and finally we do Z out, PC in and end. So, these are the following steps required when it is a unconditional branch. Let us move on and see for a conditional branch. So, for a conditional branch what happens? If the condition is met, then only it will branch, otherwise normally it will proceed to the next instruction. So, similarly here first 3 steps will be same, and finally here offset field of IR out, select Y, add Z in. Here we need to check if Z is equals to 0 or not. That means if the 0 flag is 0, is set or not. If z equals to 0, that means 0 flag is not set, and the branch instruction said branch if 0. If the 0 flag is not set, then end. No need to do anything. You can stop here, and then it will, the PC value already got incremented to the next one. So, it will fetch the next instruction as usual, and it will do it because the branch condition is not satisfied. Let us say if z is equals to 1, then what happened? We have already calculated z, this register z value here, which is offset value is added with content of PC. We will do z out, PC in, and then end. Now, PC will be loaded with the conditional branch address with this, which we have calculated using this particular offset. So, branch if 0, which is a conditional branch, a condition needs to be checked, that is here the flag, and then accordingly it will be set. If the condition is not satisfied, it will end here, and the PC will next fetch the next instruction, and if it is satisfied, then it will load the PC with the branch address. Let us see the next instruction, INC R1, where R1 is incremented by 4 and stored back in R1. First 3 will be again same. What we have to do? R1 out, select 4. If we select 4, then 4 will be selected from the mux, and which will go to one of the input of ALU. We add it, and then we put it in Z, and finally the value of Z is put it in R1 by Z out and R1 in, and finally we end. So, this is for increment. Similarly, we can have for decrement, where everything will be same, the only difference being this operation, which is sub. Here we will do R1 out, select 4, sub, and then Z in, and then Z out and R1 in. The value of Z will be put it into R1. The decremented value will be present in R1. Compare R1, R2. So, generally when we perform an operation, depending on that operation, the flags gets affected, the flags are set or reset. So, how do we compare? If we subtract these two numbers, if we subtract R1 minus R2, if the result is 0, then the 0 flag will be set. Let us say we subtract R1 R2 and the result is positive, that means R1 is greater than R2. Let us say we subtracted R1 minus R2 and the result is negative, that means R2 is greater than R1. So, depending on various condition, depending on the subtraction, various flags will get affected, and accordingly we can compare it. So, what we are doing here? We are doing R1 out, Y in, R2 out, select Y, then we do sub and then Z in. So, after sub and Z in, after the operation of ALU, flags will get affected, and accordingly we can see based on the flag value. So, depending, after performing this, we have to check a flag value to see whether R1 is greater than R2 or they are equal, or R2 is greater than R1, depending on this. The last instruction is halt. Halt will make the execution of the instruction, it will stop the execution of the instruction, but halt itself is an instruction. So, for every instruction, what we do, we fetch the instruction and then we decode the instruction. So, the first 3 steps will be same for halt, and after, at the end of step 3, once it is decoded, it is known that this is an halt instruction. So, for an halt instruction, finally what it will do? It will end. In step 4, it will end, because after performing, after fetching, then only it will decode and it will understand and it will end. So, in this lecture, we have shown basically the various instructions. We have taken a set of 12 instructions and we have shown you that how using single bus architecture we can execute these instructions. Thank you.